Hi everyone, welcome to this lecture. So this lecture is a continuation of our project 1 on support vector machine. So in the previous lecture, we learned how we can change the value of C in order to make support vector classifier as a hard classifier or a soft classifier. So we started with the large value of C, and we saw that with the large value of C, that was the value equals to 1. That is C is equals to 1. We saw that for C is equals to 1, our support vector classifier is a hard classifier. Then we reduce the value of C to 0.01. So we see that when we use the small value of C, in that case, our support vector classifier becomes the soft classifier, and more support vectors comes to join the hyperplane and the area between the decision boundary and the hyperplane. Okay, now it's time to use the kernel trick with support vector machine. So the kernel which we are going to use is the radial basis function, the RBF kernel. And when we use the kernel, then another important parameter is a gamma. So we have seen in the previous lecture that the default value of a gamma is scale. And we can also set gamma is equals to auto as well. So basically here, what we are going to do, we will change the value of gamma from scale to auto, and we will keep other values same. That is the value of kernel and the value of C, and we will see how the value of gamma and how the selection of the gamma can affect the performance of the kernel. Okay, now we are again going to instantiate the support vector classifier, but this time it is a kernel based support vector classifier. The kernel is radial basis function. The value of C is equals to 1. The gamma is scale. So let's run this cell to instantiate our kernel support vector. Here I am fitting it to our data. Okay, now I want to draw support vector hyperplanes. So this is the same function which we used in the previous lecture, draw underscore SVC underscore hyperplane. If we go back, if we scroll up, we know this is the function which is used to draw the hyperplane for the support vector classifier. Okay, now this time we are using for the kernel. So we were here. Let's draw this, and we can see that this is the support vector. Now this is our data. This is our red class, and this is our yellow class. So these are the support vectors, and this is our decision boundary. Now, basically what has happened here, basically our original data is 2D. And when we use kernel, it has projected it into a higher dimension. Then we have suppressed that higher dimension back to 2D so that we can visualize. That's why we can see this hyperplane is not in a straight line, and we also see these hyperplanes related to the class. So these are the support vectors on the hyperplane. You can see that this hyperplane has 4 support vector, and this has also 4, and here is the missing area. Okay, now this is not a straight line, and the reason is that we have suppressed the higher dimension to 2 dimension in order to do the visualization. But here the performance is very good. If we can see that this is still a hard classifier, there is no support vector between these hyperplanes and the decision boundary, and this area is empty. So when this area is empty, that is the area between the decision boundary and the hyperplanes of a class. In that case, the support vector becomes the hard classifier. So this is again the hard classifier. Now what we can do here is that we can use gamma is equals to auto now. Now let's see what will happen if gamma is equals to auto. Here I have instantiating support vector classifier with gamma is equals to auto. Here I am fitting it to my data, and here I am drawing the hyperplanes. Now we can see that in that hyperplane, it is still the hard classifier, and there is no support vector in that area between the decision boundary and the hyperplanes. But the difference is here, when we use gamma is equals to auto, it tries to learn the noise of the data and enter into the overfitting. So this is the overfitting condition. Here, the support vector is trying very hard in order to become the hard classifier. So we can see that here almost half of the data points become the support vectors, and here also the half or more than half of the data points become the support vector. So we can see that this value of gamma is equals to auto. So when gamma is equals to auto, our kernel SVM or our support vector machine enters into the overfit region. Okay, let's see if the data is not linearly separable. So here we are going to create another data set, and here we have created the noise here. So now I am using a function make underscore circle. Now this is again the function which will give us the features and the labels, but here things are different. So number of samples is equals to 100, factor is equals to 0.1, and noise here is equals to 0.05, and random state is equals to 42. So what is factor and what is noise? We will see this. First create the data and then visualize the data. So we can see that we have a data set known make circle, and using make circle we are able to generate again two labels which are in the form of circle. Okay, so this factor is important. If I set this value equals to 1 means I have increased this value. In that case, what will happen if I increase the value of factor? So the factor has to be between 0 and 1. So we cannot set the value of 1. So let's suppose its value is 0.5. Okay. So when the value of this factor is 0.5, in that case, if I plot this, so we can see that if we increase the value of the factor, in that case, there is a less separation between the data and there is more spread. Now, if I reduce its value back to 0.1, which I used initially, what will happen in that case? In that case, the separation is more. Okay, so that's why we use this value 0.1. So the noise value is 0.05. So what will happen if I do not use a noise? If noise is 0, then what will happen? Let's run this cell and see if noise. So if noise is 0, in that case, we have the perfect circles. So this will be an easy data set. So in order to make the data set more challenging, we have added the small value of noise, which is 0.05. So let's run this cell and let's visualize the data again. So this is our data, and we are going to perform the classification using kernel support vector machine. Okay, so this is the data in the form of circles. Here is the separation. So basically we need a classifier which can draw the decision boundary here between the two classes. So here we are using the radial basis function. Here I am using the value of C is equals to 5. And here I am fitting my support vector classifier to my data. Okay, now here I am observing these hyperplanes. So I am going to use the same function draw SVC hyperplane. Now look at this figure. If we see that support vector machine by using the radial basis function as a kernel has successfully performed the classification of this challenging data set. So that was our first class. That is our second class in the red color. And this is our decision boundary. This is our hyperplane for the yellow labels, and this is our hyperplane for the red label. We can see that for yellow label, we have only two support vectors, but for this label, red label, we have large number of support vector which are present on the hyperplane. So we see that when we create a data set in the form of a circle, a challenging data set, but using support vector machine or using a kernel in support vector machine, we are still able to perform the classification. And if we want to see the coordinates of the support vector, we can see that here we have a large number of support vectors. So in this project, we learn how to implement support vector machine in Python. We also learn how to implement kernel support vector machine in Python. We also learn how to change the value of C, which is equivalent to the value of K, which we studied in theory, that how to adjust the value of C in order to make the support vector as a soft classifier or as a hard classifier. Then we see how gamma affects the performance of kernel. We see that when we select a gamma is equals to scale, in that case, the performance of kernel is better as compared to the value of gamma is equals to auto. When we set gamma is equals to auto, in that case, we enter into the overfitting condition. Finally, in this project, we learned how to perform the classification when we have a challenging data set. In that case, we use the large value of C and we use a kernel, which is radial basis function. By using the large value of C and using the kernel, we were successful in order to perform the classification of this challenging data, which is a circle data. So I hope you understood each and everything of this project 1. Thanks for listening, and I will see you in the next lecture.